Hopefully I am sharing now.
We can see your slides fine, Drew. Thanks.
Fantastic. All right, moving forward. Sorry about this. Pleased today to be representing the OCI MSA. I hope to address all of Dan's points that he made, and look forward to the discussion afterwards as well. Dan and the committee had posed to us, I guess, five different questions. I'm going to focus most of the talk on the first one, and then address the four other ones at the end of the talk. Of course, discussion, as I suggested, is obviously helpful and useful. So what problem is the OCI MSA solving, or MSA? From our perspective, the sort of six industry people who got together here to create the OCI, there were three sort of main things that we were trying to accomplish here, right? We certainly needed an interconnect moving forward for optical scale up. And we'll talk about why we think that there are gaps to the existing sort of roadmaps or sort of future roadmaps or technology developments. And ideally, this thing needs to be power efficient because we're going to be start moving a lot of bits if we move to optical scale up. Multi-vendor interoperability is really key for large deployments, and I think it's something that gets missed an awful lot. We'll touch on that. And then multi-generational, so the rapid scaling that's happening in the AI world for scale up and GPU, clusters generally requires a faster level of cadence, I think, around these standards than we've seen from traditional bodies. Um, and that's a primary reason why we moved forward. And then we'll address this sort of existing MSA promise, et cetera, in the next slides. All right, so what is the OCI MSA? Six founding members: Meta, Broadcom, Microsoft, OpenAI, NVIDIA, and AMD came together, created a specification around a 200 gig bidirectional link. We announced this in March, as Dan had described earlier, focused primarily at optical scale up, but really this is an optical PHY description. We have this on the website. It's free for anyone to download. I'd encourage you to do that if you have real questions about what the technical specification is. Certainly, we're open for feedback. If you think we got something wrong, then we're interested in making it right. So we'd be certainly open to do that. The primary challenge we see is that as optical or as scale-up domains get larger, we're exceeding the bounds of what can be attached in an electrical domain, sort of a single rack, a cable length, as it were, between retimers. Moving to an optical link instead of a sort of 1 or 2 meter electrical cable allows us to disaggregate the system. Disaggregating the system allows us to increase the size of the system, and then larger scale up domains and the goodness associated with that are sort of what we think we can achieve with the OCI specification. Um, as we go across here, you can see that essentially what we would assume is that the size of the scale-up domain will now not be limited by the reach of the electrical cable, but instead by the number of ports that are available on a switch. So if you have 512 ports on a switch, you should be able to connect 512 GPUs to it, and that would create a scale-up domain of 512 GPUs. 1,000 nodes on your switch or ports on your switch, we should be able to get to 1,000, and as that progresses, we'll be able to achieve that. We made some decisions about the technology, right? NRZ signaling instead of PAM4, WDM, so this is 4 lambda by 50 gig NRZ, and then bidirectional to reduce the fiber count. All of these things associated with lower power, a path towards scalability, and reduced infrastructure costs associated with essentially is going to be a very large amount of bandwidth moving through a flat scale up to me. Okay, so one of the problems, one of the three slides I'll talk about for the problem that we're trying to address is the scaling. As I suggested or mentioned earlier, the AI GPUs are growing faster and faster. We're like on a yearly cadence for AMD. Meta's announced a 6-month cadence. I think a lot of people like NVIDIA are on a year cadence or so. Every GPU generation has a different balance or more flops. That's what we sort of pay for. But as the flops grow, the memory bandwidth has to grow, the memory capacity has to grow, and the I/O bandwidth has to grow to create and enable a balanced system. So we look at it. We have 200 gigabit per second signaling is sort of the state of the art today. We're all sort of deploying that. 100 gigabaud electrical, 100 gigabaud optical, linear solutions are possible. Fine, Bob's your uncle. We're all happy here. Um, at least we're happy that there's a technical solution there. What happens at 400 gig, which is sort of, the type of technology that we're architecting towards today? The electrical IEEE standards are out there. I think they've sort of landed on PAM4, PAM6 after a debate about PAM8 and maybe simultaneous bidirectional signaling. That probably lands in 27. 200 gig PAM4 optical is probably the solution there. Maybe there's a linear solution or not. Maybe it has to be retimed, which obviously would drive up power and drive up costs. So 400 gig sort of linear options for optical scale up are looking challenging. What happens at 800 gig, which is probably a couple of years after that? We don't know from the industry perspective where we are with that, what the signaling choices will be. I mean, we're still working to implement 400 gig. And yet, from the GPU perspective, from AI cluster perspective, that's sort of a couple of generations out. We're going to need a solution. I think from the OCI perspective, we have line of sight to what the architecture would be at 800 gig. And yet there's no line of sight to sort of standard sort of Ethernet PHYs. OCI Gen 1 today, as I described, 4 lambda by 50 NRZ, DWDM BiDi. We expect a 400 gig spec in 27, and an 800 gig spec could follow soon after that. Standard Ethernet and other sort of AUI interface processes are taking a while. It's a very complex, difficult thing. I think the IEEE spec is, somebody said to me, 1,600 pages. It takes a while to put together a 1,600 page spec, obviously. It's Bomber, it works, but there's a process associated with it. Our process and goal to drive this forward and enable these sort of GPUs and the GPU clusters is a large part of what we're trying to do. High radix switches, enabling sort of viability for high radix switches and the larger number of these lower bandwidth links is a way we're going to enable these optical scale domains into the future. As Dan mentioned, we sit here as sort of deployers of this technology and we think, well, what is the next gen scale-up interconnect? There's a lot of choices. People start talking about cone lasers and integrated lasers and external lasers and micro LEDs and VCSELs. And then you start talking about what's your modulation rate. And, you could go everywhere from 2 or 4 gig per fiber all the way up to, terabits per second per fiber. And then you start thinking about, well, I mean, coherent has a play, right? And what about DWDM? And should we do more than terahertz signaling? And then suddenly on top of that, you've got form factors, which also play into your ability and sort of how you're going to do that. And then, on top of that, what does that imply for the system architecture? It is, as Dan suggested, a bit overwhelming. And unfortunately, this is a tangled ball of yarn. Everything impacts everything else. And so looking at this being proposed at from lots of different people and having to make decisions about which technology to pursue, we saw the need to make some decisions around the technology, which would help focus developments, focus productization efforts, and enable these sort of GPU clusters, as we talked about, sort of pursuing in the future. So, okay, you make some decisions about that, but you also have to talk about sort of the ecosystem, right? There was always this discussion about how we're going to get this as a product and what is it that hyperscalers need, what is it that large purveyors of technology sort of need, and how we make that happen. I mean, I hope it's an obvious statement to say that networks require interoperable interconnect between two different endpoints. And in a standard sort of AI cluster, you'll see switch to GPU for the scale up domain and the scale out domain. But in the front end network, you also see CPUs talking to switches, as well as sort of storage networks and others. There's a plethora of sort of deployments. In the end, though, you've got two disparate sort of endpoints, usually deployed and developed by two different suppliers, which have to connect together. Our goal is to ensure that they're interoperable so that we can buy a switch from vendor A and a GPU from vendor B, and we can make sure that they can connect together and we can have a solid, reliable, low power, cost efficient, scalable interconnect. Interoperability therefore requires a common PHY spec. We've proposed the OCI spec to enable that to happen. It is not and should not require proprietary deployment. When people come to me and they say, "Oh, this is really good. We have a really great solution for one end to the link, and all you have to do is go to your switch or your GPU vendor and tell them to just adopt our technology and it'll all be fine on the other side," it's really difficult not to laugh at them. It's a very difficult position to work with, and it's why places like the OIF and the IEEE have been so successful because they don't force the marriage. They let those sort of business relationships happen on either side in a common PHY environment so that we can just pick each end. And then component systems, they're also necessary. I mean, when you talk about what these integrated optical solutions are going to look like, you've got ELSFPs, you've got fiber harnesses, you've got various sort of form factors here, finding out how to down select there and not have to have 47 different ELSFP vendors and cage sizes and other things are an important part of what we're trying to accomplish as well. So okay, I don't know how close I am on time. Maybe I talk too fast, but what are the answers to the other questions that Dan and the moderators proposed, right? Why are the existing standard bodies and consortium not solving that problem? Look, let's be clear. I think they are. They are trying. The issue we have is the rate of innovation. Power and cost efficiency for these sort of links are really associated more with front-end networks than they are with sort of very challenging scale-up domains where the competition isn't a coherent link, but is instead sort of a cabled electrical backplane. This is very low power, very low cost, and highly reliable. So we think that this is becoming a bit of a sea change in the requirements associated with the link. Additionally, there's a distributed focus, right? I mean, there are a lot of things that they're trying to do with the IEEE and the OIF, and spreading ourselves pretty thin there and trying to balance all these things became pretty challenging. Um, our MSA, the OCI MSA, is not going to produce anything, not physical. We're producing a specification to enable this interoperation. All the sort of specifications around how we would physically implement these things are going to be driven through, I think, the standards bodies. And you've seen, I think, just last week or the week before at the OIF meeting in Montreal, we proposed some changes to the ELSFP form factor to support OCI. I think you'll see efforts like that moving forward. We're certainly open and warmly welcoming of anybody helping us to sort of drive standardization around the physical realization of the OCI PHY. How does the MSA avoid stifling innovation? This one's got my hackles up. I'm almost angry at this question. I think what we're trying to do is avoid a discussion around innovation because we don't deploy innovation. We deploy products. We want productization. We want deployment. We want technologies to land in the data center and create the sort of value that we see, right, from AI, from large language models, from agentic AI. And so innovation for us is sort of a two-edged sword. Great, we want to innovate, but all the greatest innovation in the world, constructed of unobtainium doesn't land in the data center. It doesn't make anything different and land at the end of the day. We're enabling technical innovation by focusing, I think, on a market opportunity, which hopefully people will find compelling. I think, OpenAI and NVIDIA and Meta and the rest of our partners, I think that there's a valuable market here. We're certainly going to move forward and work to deploy this. We hope that you'll join us in that sort of effort towards that. Regarding the MSA, we're still figuring this out. We're trying to go fast here. Too many cooks in the kitchen is sort of a problem, but not enough cooks in the kitchen, and you sort of like create an echo chamber. We're trying to balance that out. I think you'll see things change around this and happen around this over the next 6 months or so. So I'd ask you to sort of stay tuned. And in the meantime, please feel free to reach out to any of the member companies if you have questions or concerns about sort of things and how they're working. And we're happy to sort of find a way to partner with you to enable OCI, hopefully, for everyone. Okay, that's all I have today. I don't know if Dan, you want to ask any questions? Or you
No,
just
we'll do
out?
questions at the end. That was excellent. And that was my question about how to avoid stifling innovation here. I didn't mean to get your hackles up.